Next, I'd like to do something that has to do with relativity in fields. This is sort of in lieu of doing this in class. It is a good problem, but it also explains why the field transformations work the way they do. So basically, this is the derivation of one of the field transformations. In this case, what I'm looking at is I have a particle that's moving towards a thick infinite sheet. So we'll make it infinite like that. And the sheet, like I said, is thick and it has some charge density rho. And what we're going to do is we're going to just figure out what the field from it is. I think you should be able to remember, hopefully you do remember, what the field from it is if this is not a moving charge. In a normal electrostatic situation, what this field is. In fact, it's easy enough to write. The field is E equals, let's see, we've got this guy up here, we've got some charge density rho, so sigma over 2 epsilon naught, as I recall, in the z hat direction. In this case, we have that charge density rho, so rho times the thickness, d, is going to give us the charge density sigma over 2 epsilon naught in the z hat direction. So this is what we would get if we just used Gauss's law to find the field at this point here. Nice and simple. We've done it 2 or 3 times in a couple of different situations that are all, obviously equivalent. So hopefully you're used to that by now. So this is what E is normally, and we're going to figure out what it is for this moving charge. What is the field this moving charge sees from this charged plane? Okay, and so as usual, we want to categorize all of the things that we know in this picture. All right, so we've got this infinite thick plane. So we have an infinite thick plane. And it's thick, so it has a thickness, and I called that thickness D. And it's charged, so it has a charge density. And it's a volume charge density, so we usually use rho for that. Obviously, we can use any other letter we want, but we usually use rho, so we'll keep on going with that. And let's see, we have a particle moving towards it. It's directly towards it with a speed v. And that's all we really need to know. So that's all we need to know to find the field seen by the particle. And if we call this E, we could call this other one E prime. Okay. This field is not the field seen by the particle, it's a field that the charge density would say is there. So this infinite sheet is not moving. This guy is moving with respect to it. What we're going to look at is a situation where where the particle thinks it's not moving, but it thinks that this sheet is moving towards it with some speed v. Right? So that's the whole point of relativity, is we can look at this guy or we can look at that guy. And the physical effects have to be the same, but the numerical quantities that we write down in the mathematics don't have to be the same. Our concept will be the length contraction, or Lorentz contraction. And we'll just use that, and we'll be able to find the field and we'll end up with the same field transformation that we found in class, or will find in class, depending on when you watch this. And the equation for the contraction is L prime. So the L in this situation is equal to the length in this situation is equal to the length in this situation, say this D, times 1 over the square root of V squared over C squared. Your book does a lot of things with more advanced relativistic notation. I'm not going to worry about that here. Mostly because only one of you has had a reasonable amount of relativity in the past. So throwing all those things at you might be annoying. Okay, so what are we going to do here? Well, we're doing this relativity thing. So the first thing we have to do is say, well, what happens to this plane, right? So we want to figure out what the field is, which means we want to figure out what the charge density is, right? And we might want to figure out what this distance is. To figure out what the charge density is, we're going to have to figure out what happens to this thickness. So that's the first thing I'll do, is I'll contract the plane. So I'll contract the plane. This will appear thinner when in this frame than it does in this frame. This will also appear nearer. But we won't need that right away if we need it at all. Then what I think we'll do is we'll find the new charge density. Find the charge density. So it's in the frame of the particle that we want to find that charge density, and so that's what I'll do. After that, I'll use Gauss's law to find the field. Remember that Gauss's law is sort of the fundamental way of looking at these things. In one of your problems, you'll actually use Gauss. You'll actually use the field that the book gives you for a moving particle to show that even in that case, that Gauss's law applies. So, and if it applies in that case, it applies in all cases that have things moving. So we end up with a rationale for saying that Gauss's law is there. Now, Gauss's law, as one of Maxwell's equations, really is fundamental. And it's part of the whole reason why Einstein ends up creating relativity in the first place. So, in a way, Gauss's law is one of the reasons why you end up having relativity. So it better work all the time, right? Anyways, Gauss's law we will use, and once we've found the field with Gauss's law, find the field with Gauss's law. Well, actually, I guess we want to find the flux with Gauss's law, and then we'll find the field from that. That should be pretty reasonable. So it's all pretty direct. I mean, this is a rather direct problem. I think you can see where we're going to go. So, first we want to find this d prime, right? But we know the d, and then we have this 1 minus v squared over c squared, and we're actually done. That's all we need to do in that step. Now we want to find that new charge density. So we say, okay, we have rho prime v prime, right, is equal to q prime, and q prime is equal to q, which is equal to rho v. So that's all fine, right? So let's take a look at this really closely and see what we think is going on here, right? So if we have some region here, and we have our guy coming down here, this part gets contracted, but this part doesn't. So this part is our area, right? And this part gets contracted. So if we have rho prime, A prime, D prime, A prime is just equal to A. The area part, this area here, isn't contracted, only this thickness is. So we have rho prime A times D prime. And for the situation where we're looking at it from the point of view of this guy, it's just rho AD, right? So this is the part that we want to look at. We have these two guys together. The A's are going to cancel. So that means our charge density is rho prime is going to equal D over D prime times rho. Okay. And D prime, we ended up saying, is this is D times the square root of blah blah blah. So we have rho over the square root of 1 minus V squared over C squared. Okay. So this is our charge density right here. Okay. That's the charge density that we're going to use in Gauss's law to figure out what the field is. All right. So now we're doing Gauss's law. That means we have to have some sort of Gaussian thingamabob, Gaussian surface. And usually with this plane, what we do is we have some nice regular cylindrical shape, maybe with an area on these caps of A, right? Which would be good because we have an A there already. And then height up here Z, let's say, right? This is minus Z down here, so it's symmetrical. Because whatever happens up here has to happen down there, only pointing in the opposite direction, right? So we're pretty good with that. So we'll just throw that into our Gauss's law. The enclosed charge is equal to rho times, or rho prime, excuse me, times A times the thickness here, which is D prime, right? Which is equal to rho AD times the square root of 1 minus V squared over C squared divided by the square root of 1 minus V squared over C squared. Right? Because we got from rho prime we get this one, and from D prime we get this one. So that's just rho AD, okay, which is just our original charge Q. Okay, we're okay with that. Right, that makes sense. So that's what's causing our field, and this is equal to epsilon naught times our flux by E, which is one. We count this once for each cap, times the area times the field going outwards, and because this stuff is all symmetric, the field has to be going outwards completely, and so we can use that to find our electric field. So this is actually a prime. These are all primes, I'm sorry. So where do we get this? We have E is equal to this QA rho AD over 2A epsilon naught. I forgot the epsilon naught there. These guys cancel, so and this is in the z hat prime direction, which is equal to rho d over 2 epsilon naught in the z hat prime direction. So in fact, in his frame, the particle feels exactly the same field that this guy does while he's coming down here. Basically, we've just said that E prime parallel to the surface is equal to, don't need that because this is completely unambiguous, E prime parallel to the surface is equal to E parallel to the surface, which is what we said in class, right? So we used some other sort of more abstract reasoning to get to this point in class, but it turns out to be perfectly true if you do this for a simple situation that gives you a uniform field. So we've seen now this example here, and we've seen that in class. We didn't see the companion example where the where you know you've got your particle moving parallel to this surface. That's a very good thing for you to check out yourself. You have all of the situations here. It's a good thing to do stuff yourself, and who knows what you might see in the future, right? So this has been quite good for this. Again, this plus the tangential, or not tangential, but transverse sort of thing here, where you have E hat prime is equal to E perpendicular prime is equal to E perpendicular over the square root of 1 minus V squared over C squared. Those things together will be useful when we start talking about moving charges on Wednesday. All right, Wednesday, yes. So everything here looks pretty good, and I hope that this is something that helps you with understanding why we have these different sort of field transformations in relativity, and will help you with, you know, those one or two problems on the homework where it's actually really important. So I think this will help you, and especially if you do this yourself, and I will talk to you about it in class soon. Bye now.